Welcome to Chapter 19, Part 1, Inferences about a population proportion. Now we've been dealing with inferences about population means or the difference between means. Now we're going to start talking about proportion. So this is a new parameter that we're going to be dealing with. As I said, we've been working with the mean, but now we're going to learn about the population proportion. The point estimate for the population proportion is the sample proportion, p hat. So we'll be learning about that in Chapter 19. We're going to learn how to do large sample confidence intervals for a proportion, and then we're going to learn how to do accurate confidence intervals for a proportion, choosing the sample size, and significance tests for a proportion. The proportion of a population that has some outcome, a success, is p. We have our point estimate for our parameter p hat. That's the sample proportion, and the way we find that is the number of successes in our sample divided by the total number of observations in the sample. And as you can see, in our formula, p hat equals x over n, where x is the number of successes in the sample and n is the total number of observations in the sample. So let's take a look at an example. A polling company polls 1,200 people to see if they supported a certain issue. 408 of the 1,200 supported the issue. What is the sample proportion? Well, if x is to denote the number of people who supported the issue, then in our sample, 408 of them supported the issue. And the total number in our sample was 1,200. So to find our p hat, the sample proportion, we would just say 408 divided by 1,200. And that gives us the sample proportion of 0.34, or 34%. Now, just like the mean, we can have a sampling distribution of the sample proportion. So we're going to talk about the distribution of the sample proportion. And again, because the values for each sample proportion vary from sample to sample, it's a random variable. So we can talk about what is the mean of the sample proportion, what is the standard deviation of the sample proportion, that is the sampling distribution of the sample proportion. Can we apply the central limit theorem to approximate these with normal distributions? And exactly what is the sampling distribution of the sample proportion? To define it. Well, let's answer some of these questions. Well, for a sampling distribution of the sample proportion, the mean of that is p. The standard deviation of the sample proportion, or the standard error, is the square root of p times 1 minus p divided by n. And yes, we can apply the central limit theorem, so we can approximate these with normal distributions. So we're going to be using Table A again in Chapter 19. Now, what are the conditions so that we can evoke the central limit theorem? Well, the sample size times p has to be greater than or equal to 10, and the sample size times 1 minus p has to be greater than or equal to 10, or the number of successes and failures is 15 or more. Then the sampling distribution of the sample proportion, this p hat, is approximately normal, and the mean of our sampling distribution is just p, the sample proportion, population proportion, that is, and the standard error, or the standard deviation of our sampling distribution of the sample proportion, is the square root of p times 1 minus p divided by n. So this is just a nice, concise way to write what we just wrote. So like we've done before, this is how we can get the sampling distribution of the sample proportion is we take samples of a certain size, we do it over and over and over again to find the proportion, and that creates a distribution. We call the sampling distribution of the sample proportion, and the mean of that sampling distribution of the sample proportion of size n is p, that is the population proportion, and the standard error is the square root of p times 1 minus p divided by n. In order to use Table A, however, we're going to have to standardize our p hat, our sample proportion, and the way that we do this is just like we've seen before with the z-score. P hat minus p divided by the square root of p times 1 minus p divided by n. And what is that? That's nothing more than your sample value minus the mean of the distribution divided by the standard deviation of our sampling distribution. And that's clearly seen here how they correspond to one another. It's, in general, the z-score is just your data value minus the mean of the distribution that data value came from, divided by the standard deviation of the distribution that data value came from. So let's do some work with the sampling distribution. Assume that 80% of the people taking aerobics classes are female, and a simple random sample of n equal 100 students is taken. First of all, we're going to describe the sampling distribution of the sample proportion of female students. Then we're going to find some probabilities. What's the probability that at most 75% of the students in the sample are female? What is the probability at least 90 of the students in the sample are female? And we'll ask the question, would that be unusual? And look at the difference between B and C. One is saying what's the probability that at most 75% of the students in the sample are female. That's the probability less than 0.75. But look at what part C is. It's saying what's the probability at least 90 of the students. So that's x greater than 90. So we're going to have to turn that x to a p-hat and then find our probabilities. So it will be interesting. So first we're going to take this problem and we're going to say, okay, great. Let's first of all make sure that we can do this. Is the number of failures and successes greater than or equal to 15? Or we could do the n times, that both are 10 or more. Well, we see that they are both over 15, so we're fine. So the way that we would describe our distribution is, our sampling distribution of the sample proportion is approximately normal, with a mean of 0.8. Remember, 0.8 was the probability of success. And a success is the probability that the person taking an aerobics class is a female. So the mean of our distribution is 0.8. The standard deviation is p times 1 minus p divided by n. So that would be 0.8. 1 minus p would be the 0.2 divided by n, which is 100. And you take the square root of that, which ends up being 0.04. So now we actually have our normal distribution. We know what the mean and the standard deviation is. Now we can answer the questions. What's the probability that we'd have no more than 75% female? Well, that translates to the probability that p-hat is less than 0.75. We've got to standardize our p-hat, which we're doing right here. We take our 0.75, which is our data value, minus the mean of the distribution divided by the standard error. So it would be 0.75 minus 0.8 divided by 0.04. We get the probability that z is less than 1.25, and we use table A to get that probability, 0.1056. Now the last one, remember, was the probability that x, being the number of aerobic students being female, x is greater than 90. Well, we have to change that to a proportion. So my x is 90 divided by n, or the 0.9 that you see here. So now that I have it in a proportion, p-hat greater than or equal to 0.9, I can standardize that. Make sure you too can get 2.5 when you standardize it. And then I go to my table A and I find my probability that z is greater than 2.5 is 0.0062. Now, in part 2 of Chapter 19, we're going to start talking about how to build a confidence interval about the population proportion. Because remember, that's what confidence intervals are. They're just intervals about a population parameter. But this one we're going to work with proportion. So we'll see you in part 2.